good morning. And I would like to discuss today the difference between a high redshift galaxy far, far away and the normal galaxies which we see nowadays, and a little bit talk about the disk instabilities, because I think there's a misunderstanding and things are completely different. Also, I don't really know a lot about why they are different, but that's basically what it is. If you go to high redshift, star-forming galaxies in some sense are similar to low redshift galaxies. They follow a fundamental plane, a star-forming sequence where the star formation rate is proportional to the stellar mass. And in fact, the stellar mass is not very different to present-day galaxies. It lies between 10 to 10 and 10 to 11 solar masses, maybe a few 10 to 9 solar mass galaxies. But the star formation rates, as you know, are much bigger. They are between 10 to 1,000 solar masses per year, so much, much larger than what we see nowadays. The reason for this appears to be, also I think, and nobody really understands this, the fact that the galaxies at high redshift are very gas-rich. And that is basically shown here. If you look at one of Reinhard Genzel and his group observations, then you see the gas fraction in present-day galaxies is of order a few percent, whereas if you go to the high redshift regime, then you basically have 50-60% of baryons in the gas, and therefore it seems at first likely that the star formation rates must be high. Well, you can all cast this into one simple model, which we all love and know. It's the bathtub model, which says the reason that these galaxies are gas-rich is due to the fact that they accrete gas like crazy. And so this is the old story. You have an accretion rate of gas, and the accretion rate in equilibrium is equal to what the gas which you consume, and the gas you consume is proportional to the star formation rate times 1 minus the return fraction of gas from the stars. And in addition, you lose some gas through the wind, and the wind loading factor alpha is whatever, 1 or 2, and it's probably the wind loss rate is probably all proportional to the star formation rate too. We do it like this because that makes everything simple. And then you see this is about 50%, this is about 1, so you get here a factor 1.5. And then you immediately see that the star formation rate in the galaxy is indeed proportional to the accretion rate, or the effective accretion rate, if you divide this by 1.5. So the idea has been the star formation rate must be high. This is simple, simply because the accretion rate at high redshifts is large. Now the question why these galaxies are gas-rich is more of a problem. You could say the galaxies are young, but they are not young. If you look at their stellar mass, it's 10 to 11 to 10 to 10 to 10 11 solar masses. This is very similar to present-day galaxies. They already formed an enormous amount of stars, but they are still gas-rich. So the question is, why are they gas-rich? And again, it's probably because of the accretion rate. You know, the gas mass is the accretion rates times the star formation time scale. The stellar mass is the same as in low redshift galaxies, so the gas fraction is high because the accretion rate is high. But this is too simple. This assumes that the depletion time scale or the star formation time scale is universal. It's the same for high redshift and low redshift galaxies. But why should that be so? No, the cold gas can turn into stars in 10 to 5 years. And if the depletion time scale in high redshift galaxies, for whatever reason, would be 10 to 7 years, their gas fraction would be 1% or 0.1%. So they would be gas poor. So it's due to the fact that this depletion time scale is not dependent on redshift that we get the gas-rich galaxies. And I don't think we really understand this very well. Why is the depletion time scale always 10 to 9 years and not redshift dependent and so on? Well, there's more to the high redshift galaxies, which we understand less. And this is the kinematical property. So here you see on the left side rotation where there's R1/2, half mass radius of these high redshift galaxies, and there's a very nice correlation. The rotation increases when the half mass radius increases. It's very similar to low redshift galaxies. You know, at 1 kiloparsecs, you have something like 30, 40 kilometers a second. At 10 kiloparsecs, you get to 300 kilometers a second. Similar rotation, half mass, half light radius relationship. But this is completely unexpected. The reason is...
What's the color code?
I don't go into these details. These are different redshift surveys which have been put together from Reinhardt. So these are the newest data set by Newman et al. These are the blue dots are the older since data. So that's it's all redshift 2. You know, I took out the redshift 1. They have the redshift 1 in it. The green dots are the redshift 1. Take them away out to be they. Okay, so that's similar to the low redshift, but this is not expected. The reason is at redshift 2, the universe is a factor 3 to the third power denser. Yeah? And so you would expect the rotation to be a factor 10 faster for the same radius because everything is denser, and it's not the case. So there's something really funny with these kind of galaxies. In addition, the dispersion, which you see on the right side of the gas, seems to be not dependent on R1/2. You know, it might be a little dependence, goes from 60 maybe to 50, but who cares about this minor dependence? So somehow these galaxies are all driven by high irregular motion. I wouldn't call it turbulence because I don't really know whether it's turbulence. I haven't ever seen anyone showing me a Kolmogorov spectrum, so who knows what this is. But the interesting thing is then, of course, if dispersion is constant and rotation decreases, the compact galaxies are dispersion dominated. Not because they have high dispersion, but their rotation is small, and the extended galaxies are rotation dominated. That's what it is, and we would like to understand that. Well, there has been another morphological difference claimed in high redshift galaxies, which is their clumpiness. If you look at these high redshift galaxies, often you find rings, and if you look carefully in these rings, you do find massive clumps. The clumps are of order 10 to the 9 solar masses, and the sizes of these clumps are 1 kiloparsec. And it had been claimed that this is the most important part. The clump part is what drives star formation. The star formation is happening in the clumps, and the winds which we get from these clumps might explain the outflow. So everything is now talking about clumps. Everybody now tries to understand how these clumps form. Well, there has been some understanding, but I think this is wrong. And that's why I would like to bring it up. The idea has been that galaxies always like to live at the edge of stability with a Toomres Q parameter, which is of order 1. Q is defined like that. It's a sound speed, or the velocity dispersion, if that is larger than the sound speed, times the epicyclic frequency divided by pi g surface density of the gas. And you know very well, if Q is larger than 1, then these galaxies are supported by pressure and by a centrifugal force, and so no clumps can form. And if Q becomes smaller than 1, then you actually get a range where the galaxies become unstable. They cannot be unstable on very small scales because the pressure dominates. They cannot be unstable on very large scales because you have the tidal forces. And so there's a range in radii where the galaxies are unstable. This range collapses to one single radius if Q is 1, and you get a larger range of radii when Q becomes smaller than 1. And the idea had been that these galaxies live at Q equal 1 because if they have values Q larger than 1, then there is no turbulence, no irregularities, and any turbulence dissipates, so the sigma decreases, and when sigma becomes more smaller than 1, you get lots of clumpiness, and then the sigma increases again, so the galaxies like to live at 1. Now you can cast this equation into a more convenient equation, which is shown down here. If you introduce the gas fraction, which is gas mass divided by dynamical mass, and here I assume that dark matter in the inner region is negligible, then you find that Q is square root of 2 divided by delta times sigma over V rod. And that seems to explain very nicely the high redshift galaxies. You know, delta is of order 0.5, and so you see immediately that the sigma must be large in these galaxies because, you know, you get something sigma over V rod of order 20-30%. The fastest growing wavelength, which is just the wavelength which can grow at Q equal 1, is then delta times R, which of course is of order the disk scale length. R is the disk scale length, and the mass of the clumps goes as delta square. And so if you have delta of order 0.3, then the mass of the clumps is typically 10% of the disk, which is also large. So that was the idea behind this Q equal 1 business. But I think it is not working. Why is it not working? Well, linear theory does not apply. This is linear theory. But these galaxies are not linear. When you look at the clumpiness, you can say they are just right now becoming nonlinear, so we are still seeing linear theory, but it's wrong. They have already 10 to 11 solar masses of stars. They have been nonlinear for quite a long time to form all of these stars. This is a theory that leads to rings, but galaxies are not axisymmetric. We do not see rings, we see clumps. Sometimes the clumps are in the ring, but the clumps are the properties which we want to understand. It's not clear whether a disk that once has become unstable and then you generate irregularities and Q goes above 1 formally should be stabilized again. I have never seen this in any simulation. So who knows, once a disk is unstable, it might be unstable forever. So this is also not clear. Then, if you take this for granted and say delta is of order 0.5, you would expect sigma to be proportional to V rod. But that's not the case. V rod changes from 20 kilometers a second to 400 kilometers a second. Sigma is always 60. It's not what you would expect from this relationship. Finally, most of the molecular mass is not in the massive clumps. The clumps have 10 to the 9 solar masses. We have 5, 6 clumps. 6 10 to the 9 solar masses. But the galaxies have 6 10 to the 10 solar masses of gas, molecular gas. So actually most of the gas is not in the clumps. And that might mean most of the star formation doesn't happen in the clumps, but happens in between the clumps, there's things which we don't resolve. And finally, if you do this Toomres instability business, and Avishai has written several papers on that, then you show that the clump should be fast rotating, because they feed from the shear flow of the galaxy disk, and this is not being observed. So something seems to be completely different. Now, because of that, I hired a graduate student. Yeah, Marcella? For the big galaxies?
How do you know that the clumps are not rotating?
Well, this is what. There's a long debate between Avishai and Reinhard on that, and you better ask him. I keep out of this. It's nice to sit with a glass of beer next to them and let them talk and you drink, but I don't get into this business because it's. Yes, they rotate much less than what you would expect. That's at least you can say. There might be some rotation, but it's not that V over sigma is of order 1 or so, it's of order 2 or so. It's maybe of order 1, yeah. Yeah, that's what he says. Well, I will tell you that this tumor business is wrong anyway, so don't worry about it anymore. It's, who cares about this? It's not, okay. And this is a work that has been done by Manuel Berenbaum. He's a graduate student of mine, and he's now looking into this, and we say we do the most simple case. We don't do cosmology, don't resolve the scales, and then put a lot of mess in it, and then get the mess out, and then don't know what, we can get everything, or did we do any physics? We do a very simple case, take a disk, unstable, homogeneous, smooth, and see what happens. This has been done by Frédéric Bruneau before, and we wanted to do it again. And so we started with a smooth disk. You can see this is quite smooth. A scale length of 16 kiloparsec, and a disk rate is 16 kiloparsec, scale length of 5, a mass of 3 × 10^10, embedded in an environment which mimics a dark matter halo. It's a constant rotation curve roughly with 10^11, so delta is 0.3, and we used Ramses. And the first thing we noticed is it is very hard to resolve the disk scale length. The disk scale length, if you would have 10K gas, is tiny. It's very, very small, and we found out that you need to resolve the scale length with at least 5 to 10 grid cells to get the scale height, scale height, with 5 to 10 grid cells to make any sense. And that would be if you would take a 10K gas of order a few AU, maybe 100 AU, so yeah. So too small to resolve. Now people say this, I don't care, I'd never resolve it, and later on turbulence forms and whatever irregularities, and they drive then the scale height up. But if they do it that way, and then they later on resolve it, they might have done something completely wrong. If they would have resolved the scale height from the initial condition, they would never had gotten turbulence. So you start with the wrong initial condition, you get something out, which later on you can resolve, but are you really doing the right thing? I'm not sure. So we wanted to do it correctly, and that means in order to resolve the scale height, with this kind of resolution, we had to start with 10 to the 4 Kelvin, not 100 Kelvin or 10 Kelvin would never resolve it. 10 to the 4 Kelvin, we kept it isothermal to do it in a simple way, and then looked what happened. Well, what do you expect? How many structures do you expect? You know, delta, I said, is around 0.3. You expect roughly then 10 structures, 10 clumps to form. This is the tumor Q, which you have in this kind of environment. And if you know Q, then you can basically, you see it goes above 1 at a radius about 11 kiloparsecs. We wouldn't expect any instabilities out there. Here we would expect instability. And actually you can work out, if you know Q and the kappa, you can work out what the fastest growing wavelength is. And you see it's here of order half a kiloparsec, and then it increases to about 10 kiloparsecs. So this is the fastest growing wavelength, but these wavelengths would also grow. They are growing with less rate, so less fast. And the interesting question is, this is kind of the range of growth out here stable. And the question is this fastest growing wavelength winning, or do the other ones take over? So who knows? So that's why we wanted to understand it. Okay, once you know the fastest growing wavelength, then you can fix the inner ring, and then you can work out what the next ring can form, because the inner ring has a thickness of the fastest growing wavelength. And then you get the next ring, and the next ring, you can work out how many rings you could form, and you come up with about 11 rings. It's roughly delta, 1 over delta square, as I said. So this is 11 structures that you can form. And in fact, if you do the simulations, this is exactly what we find. We find exactly this, the separation of rings as shown here. So that was a very nice confirmation of, but if you don't resolve the scale height, you don't get anything like that. It's a complete mess, it's all wrong. You all really have to resolve the scale height to get that. It's isothermal, yes. Well, let's just do it because it's simple test, a simple theoretical investigation. It's not the high redshift galaxies, but I don't care. I won't understand. Yeah, I told you reality in a second. Wait a minute, I tell you what I learned from this. Yeah? Okay, I tell you what it means in a second. Yeah? Okay, so this is how the thing evolves. And you basically see what happens. You form the inner rings first because the collapse time scale or the tumor time scale is shorter. And then the rings are actually breaking up into fragments, and then you form rings further and further out. What happens is the rings collapse onto themselves on a certain time scale and then form clumps. And while the outer clumps are just beginning to form, the inner clumps are beginning to merge. So what you see already here is the simple arguments we always present is we should expect 11 clumps. But obviously, you do not form 11 clumps. You form many, many more. Why do you form many more? Because the clump formation happens when the rings have collapsed into a thin line, and the thin line fragments. Its Jeans length, wait a minute, its Jeans length is much smaller than the original Jeans length or the original tumor length, and therefore the number of fragments you get is much, much, much more. So you cannot use a simple delta argument. They are very tiny, yes? They are very tiny, and later on they grow. And of course they grow, but it's a completely different process. It's not tumor instability anymore. It's merging of clumps. It's a completely physics that we are talking about to get to big clumps. It's not the tumor argument that you can use. So that's the first thing which we learned. We also looked at the wavelengths, and I said we have several wavelengths and that can grow, but only the fastest growing wavelength takes over, so that works very nicely, so that you can use to work out where your rings are forming, and you can show that actually the other wavelengths go less fast. The other wavelengths all perfectly in agreement with tumor as long as your axis is symmetric. But once you break up, the whole situation is very different. Interesting was when these rings began to collapse onto themselves. People usually use the tumor time scale to tell us when fragments should form. But we find that the collapse time scale, which is given here, this is the numerical result, and this is the tumor time scale, is 10 times longer. It's of order a few 10 to the 8 years, not a few 10 to the 7 years. So if you really want to calculate how quickly your disk fragments, you should use a time scale which is 10 times longer, not the tumor time scale. That is maybe of some interest. Here is what happens in details. These are the density maxima, and you see here the rings forming at the distances as we would expect them. This is when the rings collapse onto themselves and begin to fragment, and then you get a whole mess. This is what we call turbulent state of a galaxy. This is the initial linear state of a galaxy. And the question of course, is this mess at all related to the Toomres analysis, which we always use? These simple formulas which we use, which are kind of based on the linear stability analysis, do we get something similar for magical reason, or is this mess leading to something completely different? So the first thing is we looked at the number of clumps. As I said, we would expect 9 clumps to form, but we got much more, and here's the evolution. You see how many clumps, you see when another ring becomes unstable, you see a peak in the clump formation, because here, this ring becomes unstable, then this ring becomes unstable, and here you see how many clumps you have as a function of disk radius. And you see you get in the instability first a lot of clumps, but then the clumps begin to merge, and after some time, the system has fragmented, and then you get a constant number of clumps. It's not such that the clumps merge and merge and merge, and you get less and less clumps. The reason is the most massive clumps are disrupted again. If the clumps become larger than the tidal radius in the galaxy, they break up again. So you get a continuous structure, basically, at the very end of order 150 clumps. That's the equilibrium. It's much more than you would have predicted from Toomres, and it's an equilibrium situation. This is the clump mass distribution. This is where we would expect it to have been from Toomres instability. And you see it's completely different. Initially we get small clumps, but of course the massive clumps grow by merging. But once they reach this Toomres mass, which is interesting, they break up. There are not many forming out there. They break up again. So the Toomres mass is indeed interesting. It tells us the most massive clump that ever can form. But it's not the typical mass of the clumps. Most of the molecular gases is much smaller clumps, and only a few 5 or 6 massive clumps are forming. That's exactly what the observers tell us. But the observers say this is where the action happens. And I would say here's where the action happens. So this is the diffuse part, which is 10 times more than the clump mass, which the observers don't resolve. And if you want to understand the high redshift galaxies, look at this here, and don't look at this here. This is interesting, but not interesting if you want to understand the evolution of the whole galaxies. Where you see the mass-size relationship of these clumps. The size is given by this complex kinematics, because the clumps have substructure. And interesting enough, you form a mass-size relation, m goes as r square. I don't know why, it just happens to be so. And you see this is well established, and once it's established, it stays like that. The red dot is the mean size and the mean mass, so to say. Average, and you see you get an equilibrium. The clumps get sizes of kiloparsec. The most massive clumps have a size of a kiloparsec and a mass of 10 to the 9. And then they break up and start down there again and do the whole cycling again. You get something in equilibrium. It's very nice. You get the nothing, but most action happens again down there. So I would say Toomres somehow works in an unstable disk, but only as an upper limit. That's all you can learn from this. Well, here you have a little more details of, you see basically the colors show you how massive the clumps are, and you see how they form in these rings. There's another ring-like structure forming, and then you can look where your massive clumps are, and you will see they are all over the place. They are not always in the inner region. Of course, there are some in the inner region, and in the later on, you get also some in the outer regions. This is maybe of less importance. Now, let's look at the velocity dispersion. What happens to the velocity dispersion? Which is the irregular motion of the clumps. And indeed, you see that the velocity dispersion is increasing. It's starting very small, and it's going up, and it reaches of order 40, 50 kilometers a second. This is roughly what you would expect from Toomres instability. But I told you, it's not the simple Toomres theory. It's something more complex. Still, you get roughly the right dispersion. It's a little off, but you get roughly the right way. What is the Toomres Q? Initially, it is of order 0.5, 0.6. It grows, and then it reaches actually a plateau at 1. But once the rings break up, this is still Toomres instability, so this works. But then the rings break up, and then you see the Q does all kinds of things. So it stays of order 1-ish, but it's not 1-ish. It's I told you I'll try to keep to the time. So I'm done anyway. But it's more like 2, and I wouldn't say this is what you would expect. This is a highly nonlinear case. Why should Q be smaller than 1? It can be larger than 1. So I'm not sure what it all means and so on, but basically I would say one has to be a little careful with this. And I'm at the end of my talk anyway. So what I would say, the Toomres theory correctly predicts the growth of rings. Rings in an unstable disk situation are like this, and some of the clumps are seen in rings, so maybe these rings are the leftover parts of a linear stability. And also we get the right number of perturbations, and the vastest growing wavelength is always wing, and this is okay. The collapse time of the rings to form clumps is 9 times the Toomres time scale, whatever this is worth and interesting for. And then the fragmentation of rings leads to a number of clumps. How many clumps form depend on how thin the rings are. How thin the rings are depends either on your resolution or your thermodynamics. The rings would collapse to an infinitely thin spindle if they could, and then you get an infinite number of clumps. So, because the size of the clumps is given by the thickness of the ring. So, I could get any number of clumps depending on whether I read the rings up or whatever I do. So, this is something which is not determined by the Toomres theory. And the fragments are initially small, despite Q being of order 1, but then they begin to grow. And fascinating enough, the most massive clump is actually exactly what you predict from Toomres theory, which is maybe due to the fact that more massive clumps, as Toomres would also say, are tidally torn apart, so they can't grow beyond a certain size and mass. And that you get at the end a self-regulated time-independent clump mass spectrum and size distribution, which is not dominated by the massive clumps. They are only the tip of the iceberg, and this is where the action happens, which Reinhard can't see in his observations, and the Kendall's team probably also cannot see. And so this is something which I think is most important. The Toomres theory does not apply to the observed high redshift nonlinear phase of these star-forming galaxies. In general, also, we might learn something using Toomres. Okay, so that's what I would like to say and thank you for listening. This is rare. Let me say, this is rare that he doesn't disagree. But he formulated it not I agree. He said I do not disagree, which is already okay, Mark, sorry.
This seems like exactly the picture we have for giant molecular cloud formation in the Milky Way.
Yes.
It's exactly the same in that you see a very broad mass spectrum. The tip of that mass spectrum is about the Toomres mass.
Precisely right.
The reason that you can get very small masses is the fact that the gas is isothermal or even sub-isothermal. And as you said, that can fragment to infinitely small masses. Your simulations aren't converged, and they can't possibly be converged because isothermal fragmentation doesn't have convergence.
Sure. I know, it's exactly the case. We get a peak in the mass spectrum, but we don't resolve the low mass clumps. If we would resolve, we probably would get a power law distribution of masses. Exactly. So in some sense, the high redshift galaxies are not different than low redshift galaxies. They have more massive clumps because they have more mass. And so n equal 1 is reached at higher masses. Yeah, that is my story. This is exactly, so they are similar, but the most of the action happens not in the most massive clumps, but
then why does that mean you can't use Toomres theory for local galaxies?
because why does it, well, okay, yeah. Why does it work for Toomres? Yeah, I think the Toomres has included this condition that clumps are disrupted when they are too large. This is part of Toomres. And so that explains why the most massive clumps are at the Toomres limit. I think that makes sense. But why the dispersion is similar to Toomres, I don't know. To Q equal 1 or 2, I don't know. This random motion of the clumps, why that regulates to something Q of 1 and 2, I don't know yet. This is a random n-body simulation with merging and correlation and dispersion. This has to be worked out.
Let's get another question.
Yes.
Yes.
About your simulation, did you perform your simulation in gas core case or pure n-body case? So I think if the disk is pure n-body, clumps cannot form because no dispersion.
Well, no, still. Well, if you start with a very cold n-body disk, particle disk, immediately you get clumps.
Yes, I think there might be gas fluxes flash from clumps.
There might be what, I guess?
Gas fluxes flash to form clumps.
Yeah, okay, well, you don't have the pressure the thermal pressure in the gas in the stellar simulations, but the thermal pressure is small compared to the turbulence anyway in this case. So I think the initial Toomres instability would be almost exactly the same if you would do it with an n-body system. But later on, the clump evolution and the breakup and all of these things are different, of course, because that is given by pressure and all kinds of effects. Also, the fragmentation of the rings depends on internal pressure, which in this n-body simulations doesn't exist. So the fragmentation of the rings indeed might be a thermodynamical effect, where the rings break up, heat up. So I agree.
Why don't you get ready for the next talk, and Joel has a question.
So I'm not at all sure that these simulations have anything to do with high redshift galaxies. High redshift galaxies do not have thin disks. In fact, many of them don't have disks at all. They're elongated.
These disks are not thin.
So what we have discovered, the simulations without and then with radiated feedback, is that without radiated feedback, we have a number of clumps that's very similar to what you showed. Lots and lots of small clumps, and a few massive ones. With radiated feedback, the small clumps are simply not there. The clumps are not smaller than about 10 to the 8. They're all in the range of about 10 to the 8 to 10 to the 9 solar masses, and the disks are thick. And that doesn't seem to be in accord with what you're doing. And the reason I assume is that there's a lot of pressure being put into the gas.
Radiation pressure is not in, and it might change the subject, but we now basically can put it in. We can now redo the things with radiation pressure and the magnetic fields or what you want, and see how they change the picture.
It may still be that a simple Toomres analysis doesn't apply.
Yeah.
But
who knows?
The story of
Yes.
fragmentation and
But the disks are, yes.
is not something that happens with radiated.
The disks are thick in the sense this is what we would predict for the thin Toomres instability disk. And you don't see it, and so basically you need to take this effect into account that the disks have a thickness and not infinitely thin. But I agree with you, there are additional, Marcella is completely right, of course. It's, you can put in lots of physics now, but I thought the first things I learned from this, I hadn't known before. Yeah, this kind of equilibrium structure and the most massive clumps being the Toomres mass, I didn't know before, so I learned something from this, and I want to share it with you. And now you know this, now I can tell you more complex situations. But I'm always just doing the complex part and not understanding the basics I don't like so much.
Okay, let's thank Andreas again.
Probably all proportional to the star formation rate 2. We do it like this because that makes everything simple. And then you see this is about 50%. This is about 1, so you get here a factor 1.5. And then you immediately see that the star formation rate in the galaxy is indeed proportional to the accretion rate, or the effective accretion rate, if you divide this by 1.5. So the idea has been the star formation rate must be high. This is simple, simply because the accretion rate at high redshifts is large. Now, the question why these galaxies are gas-rich is more of a problem. You could say the galaxies are young, but they are not young. If you look at their stellar mass, it's 10 to 11 to 10 to 10 to 10 11 solar masses. This is very similar to present-day galaxies. They already formed an enormous amount of stars, but they are still gas-rich. So the question is, why are they gas-rich? And again, it's probably because of the accretion rate. You know, the gas mass is the accretion rates times the star formation time scale. The stellar mass is the same as in low redshift galaxies, so the gas fraction is high because the accretion rate is high. But this is too simple. This assumes that the depletion time scale or the star formation time scale unexpected. The reason is,
What's the color code?
I don't go into these details. These are different redshift surveys which have been put together from Reinhardt. So these are the newest data set by Newman et al. These are the blue dots are the older since data. So that's it's all redshift 2. You know, I took out the redshift 1. They have the redshift 1 in it. The green dots are the redshift 1. Take them away out with a. Okay, so that's similar to the low redshift, but this is not expected. The reason is at redshift 2 the universe is a factor 3 to the third power denser. Yeah? And so you would expect the rotation to be a factor 10 faster for the same radius, because everything is denser, and it's not the case. So there's something really funny with these kind of galaxies. In addition, the dispersion, which you see on the right side of the gas, seems to be not dependent on R1/2. You know, it might be a little dependence, goes from 60 maybe to 50, but who cares about this minor dependence? So somehow these galaxies are all driven by Good morning, and I would like to discuss today the difference between a high redshift galaxy far, far away and the normal galaxies which we see nowadays, and a little bit talk about the disk instabilities, because I think there's a misunderstanding and things are completely different. Also, I don't really know a lot about why they are different, but that's basically what it is. If you go to high redshift, star-forming galaxies in some sense are similar to low redshift galaxies. They follow a fundamental plane, you know, a star-forming sequence where the star formation rate is proportional to the stellar mass. And in fact, the stellar mass is not very different to present-day galaxies. It lies between 10 to the 10 and 10 to the 11 solar masses, maybe a few 10 to the 9 solar mass galaxies. But the star formation rates, as you know, are much bigger. They are between 10 to 1,000 solar masses per year, so much, much larger than what we see nowadays. The reason for this appears to be, also I think, and nobody really understands this, the fact that the galaxies at high redshift are very gas-rich. And that is basically shown here. If you look at one of Reinhard Genzel and his group observations, then you see the gas fraction in present-day galaxies is of order a few percent, whereas if you go to the high redshift regime, then you basically have 50–60% of baryons in the gas, and therefore it seems at first likely that the star formation rates must be high. Well, you can all cast this into one simple model, which we all love and know. It's the bathtub model, which says the reason that these galaxies are gas-rich is due to the fact that they accrete gas like crazy. And so this is the old story. You have an accretion rate of gas, and the accretion rate in equilibrium is equal to what the gas which you consume, and the gas you consume is proportional to the star formation rate times 1 minus the return fraction of gas from the stars. And in addition, you lose some gas through the wind, and the wind loading factor alpha is whatever, 1 or 2, and it's probably the wind loss rate is universal. It's the same for high redshift and low redshift galaxies. But why should that be so? No, the gas, cold gas, can turn into stars in 10 to 5 years. And if the depletion time scale in high redshift galaxies, for whatever reason, would be 10 to 7 years, their gas fraction would be 1% or 0.1%. So they would be gas poor. So it's due to the fact that this depletion time scale is not dependent on redshift that we get the gas-rich galaxies. And I don't think we really understand this very well. Why is the depletion time scale always 10 to 9 years and not redshift dependent and so on? Well, there's more to the high redshift galaxies, which we understand less. And this is the kinematical property. So here you see on the left side rotation where there's R1/2, half mass radius of these high redshift galaxies, and there's a very nice correlation. The rotation increases when the half mass radius increases. It's very similar to low redshift galaxies. You know, at 1 kiloparsecs, you have something like 30–40 kilometers a second. At 10 kiloparsecs, you get to 300 kilometers a second. Similar rotation, half mass, half light radius relationship. But this is completely